You've all heard of Moore's Law, but have you heard of Dennard's Law? IBM's Robert Dennard invented the one capacitor, one transistor concept that makes up DRAM, and such a thing sufficiently establishes a semiconductor legacy. But there is one more thing. The man defined a decade of semiconductor scaling. In this video, we explore a scaling trend that lifted an entire industry. In the early 1970s, Robert Dennard and a team of IBMers were assigned to a research program to take advantage of Dennard's recently proposed one-transistor DRAM idea, which at the time nobody had yet implemented. The program's very aggressive goal was to cut memory costs to about $0.00001, or 1/100,000th of a dollar, per bit of data. This was hundreds of times the existing rate, so very ambitious. The team did some math and realized that they would have to shrink that one MOSFET transistor in the DRAM design to about 1 micrometer between the source and the drain. This was crazy small considering that length was around 5 micrometers then. Would such a device work? Or would the source and the drain get so close together that they merge? In such a situation, the charge carriers would punch through the gate and make it impossible to turn the whole thing off. Dennard and the team wondered what might happen if they reduced all of the transistor's dimensions by the same factor and lowered the voltage by the same factor. If they do it right, some special doping treatment via ion implantation was necessary, then the transistor should operate the exact same way, right? Dennard's associate, Hua Nianyu, who would go on to play a major role in Taiwan's semiconductor industry, built a few of these 1 micrometer transistors. The team measured them and found that the transistor worked almost exactly the same. A MOSFET works by creating an electric field to compel charge carriers to cross from the source to the drain, or, as they call it, the channel. That electric field strength can be derived by dividing the voltage by the channel distance. Scale down the voltage and the channel distance by the same amount, and the electric field's strength remains constant. Thusly, this new field can drive just as many charge carriers across the channel. Dennard also opened the door to getting faster switching transistors at less power. When studying the scaled-down transistor, they discovered two different things. First, the transistor switched way faster than its larger brethren. This makes intuitive sense. The charge carrier is still going as fast as it went before, but now it travels a shorter distance between source and drain. And since the voltage is now smaller, the smaller transistor also does not consume as much power. There is a formula, as there often is. The amount of power that a transistor uses while switching is called dynamic or switching power. It is one of the transistor's major demand sources of power, and is a function of capacitance, supply voltage squared, and switching frequency. If you can shrink the transistor and thus lower the supply voltage, then we can scale up the switching frequency without greatly impacting overall switching power. And since switching power is where the transistor most uses power, well, then this is great. Imagine an IC with 10 transistors consuming some X amount of power. We shrink the size of each transistor so to allow us to double the number of transistors on the IC to 20. We get all the benefits of the shrink. But now, despite there being twice as many transistors on the IC, the whole thing still only uses X amount of power. It's a miracle. Dennard and his team actually first published this result in 1972 and gave a talk at the International Electron Devices meeting. He recalls in his oral history with the Computer History Museum that when he talked about scaling the gate oxide, which is the layer of oxide between the gate and the channel, from 100 nanometers to 20 nanometers, people laughed. 2 years later, the IBM team published a paper dryly titled The Design of Ion-Implanted MOSFETs with Very Small Physical Dimensions, the IEEE Journal of Solid-State Circuits. It became the journal's most cited article. The team wanted to express their results in an easy way, so they came up with a single dimensionless scaling factor called K, and they stuck it into a table. Thus we have the famous statement that if we scaled down a transistor by K scaling factor, then the voltage to supply that smaller transistor also scales down by that same K. That idea worked, and we now have Dennard scaling, or Dennard's law. Engineers realized the value of Dennard scaling, particularly when combined with a new type of MOSFET, complementary metal oxide semiconductors, or CMOS. CMOS devices are made up of a combination of N-type MOS and P-type MOS transistors. They are largely the same, except one transports negatively charged electrons and the other positively charged electron holes. Dennard scaling implied that if we can scale the transistors on a CMOS device by 10 times, then the device then gets 10 times faster. But for a long time, however, the problem was the power supply voltage. Throughout semiconductor history, we supplied the transistor gate with 5 volts. This was largely for practical industry reasons relating to the circuit board. Why is this a problem? If the gate length shrinks too much without the voltage scaling down, then the electric field gets so powerful that it damages the gate. 5 volts was simply too high a voltage. This limitation meant that most people used CMOS for low-cost applications where performance is not needed. But then in the early 1990s, the industries got together and hashed out a roadmap to reduce the voltages. Realizing that this was important to CMOS scaling, voltages rapidly fell down from 5 volts to 1.2 or even 1 volts. It effectively allowed us to make better CMOS at cost, since we don't have to harden the CMOS against very strong electric fields, and unleash the golden age of Dennard scaling. Dennard scaling drove the CPU industry through some of its greatest years. Then, in the late 1990s, Intel CPU transistors shrank extremely rapidly, enabled by the insertion of new 193nm DUV lithography tools. The shrink was so rapid that things hit a wall. The issue was that the industry's rules for Dennard scaling had several silent assumptions. Importantly, it assumed that we can continue physically shrinking every part of the transistor without issue. We did for a while, but then the gate oxides got to be something like 5 nanometers thick. Remember when people laughed at the idea of the oxide being 4 times that thickness? And then the channel lengths got to be about 25 nanometers long. New issues with doping made it impossible to shrink that any further. More importantly, Dennard scaling said nothing about sub-threshold leakage. Sub-threshold leakage is the residual current that persists even when the voltage applied to the transistor is below the threshold voltage, supposedly shutting the gate. The lower we try to scale the threshold voltage, the worse the leakage gets. At the 90 nanometer node at the turn of the century, leakage took up about 30% of a transistor's total power draw. This not only makes the transistor quite energy inefficient, but also quite hot. Worse yet, one of the factors affecting leakage is heat itself. As the transistor gets hotter, the threshold voltage falls, which makes the sub-threshold leakage worse. Leakage rises 2% for each Celsius degree increase in temperature, so heat begets more heat. CPU chip transistor temperatures were on the rise even in the years leading up to the 90 nanometer node, but 90 nanometers was a step up, with transistor temperatures up an estimated 4.5 times from during the 350 nanometer era. Back in 2003, the Semiconductor Industry's International Technology Roadmap projected that, by 2018, we would have chips with 53 GHz single-core chip frequencies. But thanks to these power and heat issues, we cannot easily deliver more power to the chips without effort and trade-offs. As a result, frequencies have generally topped out at 4 GHz per core since 2006. They call this slowing progress the power wall. In response to this, the semiconductor companies introduced the concept of parallelization, or the multi-core era. This is where you split up a job and have many cores multitask on them. The first commercially available chip with multiple cores was the IBM Power 4, released all the way back in 2001. After that, there was AMD's dual-core Opteron in 2004, and then Intel's Pentium D in 2005. AMD's VP Dirk Meyer said at the time, "Dual-core technology provides an attractive path for increasing processor performance with little or no increase in power consumption or heat dissipation." But the multi-core era caught software programmers unawares. Very famously, there was this 2005 article by Herb Sutter called "The Free Lunch is Over" that observed that most classes of applications enjoyed free and regular performance gains without doing anything special, simply because the CPUs got faster. The end of Dennard scaling ended the free lunch. Pressured by the market, the CPU makers charged into the multi-core era, but doing so required rolling back a lot of the tricks they employed before to get single core to those speeds. These rollbacks broke old programs and exposed security threats. Few programs at the time were entirely parallelized, mostly like high-end simulations for supercomputers. And even after that parallelization effort, there's only so much speedup you can get out of a rewrite per a computer architecture principle called Amdahl's law. Thus, it took a significant amount of time, years even, for vendors to reprogram their software to take advantage of this concurrency. More concerns emerged about the sustainability of the multi-core era. In the early 2010s, as the chip industry aggressively pushed up the number of cores, a team led by Hadi Esmailzadeh at UC San Diego introduced the concept of dark silicon. In a dark silicon world, Moore's law still lets us stuff ever more transistors onto the chips at a rate of about double every 2 or 3 years. However, onerous power and heat limits mean that we have to be constantly shutting all power to significant percentages of those chips, leaving them quote-unquote dark, maybe as much as 93% per the predictions at the time. Such a scenario adds pressure on designers to allocate resources in a smart way to avoid hotspots while also doing the task quickly and efficiently. The interpretation then was that even if we can put more transistors onto the chips, what was the point if we can't light them all up at the same time? As it often is, things did not quite go the same way of the dark silicon apocalypse. It's still possible to scale down the transistors without increasing leakage. Dennard scaling was just a very easy way to make it happen. New innovations like the high-K metal gate, silicon on insulator, or the FinFET have picked up the baton. And ahead, we still have things like nanosheet. And Dennard's ending has helped us to move beyond the big dominant compute paradigms of the 1990s, where everything was single-thread and CPU-centric. Being unable to rely on a single generalized chip always being able to run everything program faster and faster eventually pushed designers towards the system-on-chip paradigm where functions are handled by a multitude of different sections. During operations, not all of these sections are lit up at the same time. The parts not in immediate use are quote-unquote dimmed, meaning instead of a total shutdown, they might be underclocked or turned into a cache. An example of this is ARM's big little paradigm, where 4 high-performance A15 cores will work until the thermal limit is breached, then they switch to more efficient but low-performance A7 cores. This worked extremely well during the mobile boom of the 2010s when power was at a premium. And then, of course, we had the emergence of the deep learning era in 2012. GPU hardware, like those from NVIDIA, promised to take full advantage of the parallelism and large core counts promised nearly 10 years earlier at the start of the multi-core era. Looking back at it, Dennard's end and the start of the multi-core era were far more momentous than we think. It was a turning point in the technology industry and allowed for more diversified forms of compute. If we had been able to scale single core forever and eventually got to those 53 GHz CPUs, I wonder if GPUs and the like would be anywhere near as dominant as they are now. The impending physical limits marking the end of Dennard scaling had been obvious for a long time. It was easy to see that there was a limit to how thin the gate oxide can get or how short the channel can be made. Why did the end of Dennard still hit the industry in the face then? I'm not entirely sure, but I stumbled across an interesting thread on the excellent SemiWiki website. It pointed me to a February 2004 talk given at Stanford by Bob Colwell. Colwell was chief architect of Intel's IA32 microprocessors from 1992 to 2000. I could not track down a recording of the talk titled Things CPU Architects Need to Think About, but the thread author wrote, and I quote, Bob Colwell mentioned during this talk that one of the reasons he left Intel, after being chief architect on the Pentium 4, was in part because he had been told to execute on, quote, higher clock speeds, end quote, for the follow-up designs which were entirely dependent on Dennard scaling not being dead. For that reason, and thermal density, he claims he saw the writing on the wall, declined to do it, and that was part of why he left Intel. I went into Colwell's oral history, and what he said there kind of makes it sound like the case. Quote, the last year I was there, I was not in the microprocessor group anymore because I had parted company due to my disagreements and vision with the top brass, and I did not want to work on the follow-up to the Pentium 4, which eventually became Prescott. I didn't think it was going to be a great product, and going further down a path that I thought was technologically finished, a dead end. What I'm guessing what happened is that Intel found itself chasing one thing: execution speed. They chased it to such an extent that in the final years, gate length shrank even faster than the rest of the transistor. I think Intel got hooked on this one single thing, and their control of it, in my opinion, kept their thumb on the rest of the industry. Once it ended, the industry changed forever. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.